Hello everyone. In this video we're going to cover section 6.6 and this will likely be the last section that we cover for the semester. So what we're going to do is we're going to introduce inverse trigonometric functions and how to compute values of inverse trig functions. So the first thing we need to recall is that if we're going to define inverse trig functions, well then you need to have a one-to-one function. But if you look here at the graphs of some of the functions that I've drawn for you, here's sine, cosine, tangent. Of course, you could also draw cosecant, secant, and cotangent as well. You'll notice that these functions are not one-to-one. So, like, look here. This function, the sine function, does not pass the horizontal line test, nor does the cosine, and nor does the tangent, right? You see here, like, if you put a horizontal line, you get passing to the graph multiple times. However, if we try to find just a section of the domain where the graph passes the horizontal line test, then we'll use that instead. So I think it's easiest to see actually with tangent. And so here with tangent, you'll notice that as long as I'm between like minus pi over 2 and pi over 2, I get this nice curve that passes the horizontal, or it passes the horizontal line test, right? So in fact, what we're going to do is we're going to just forget about everything else and only restrict our domain here to minus pi over 2 to pi over 2. Now let's go over to sine and see what we have to do. Well, there's a few choices you can make, but essentially you either want to be use a part of the domain where the function goes like up from minus 1 to 1, or down from 1 to minus 1, right? So you see like here, if we start at minus pi over 2 and end at pi over 2, notice the graph of the function increases just like so and passes the horizontal line test just on this piece here from minus pi over 2 to pi over 2. And so that's actually what we're going to do, is we're going to restrict the domain from minus pi over 2 to pi over 2. And the range then, well, it'll be from minus 1 to 1, right? All the y values that are hit, that's the range, so minus 1 to 1. Okay, let's look at cosine now. I think what we see is that if we start at 0 and end at pi, then the graph it decreases the whole way, and you'll notice that it passes the horizontal line test just on 0 to pi. So, restrict domain to 0 to pi. And of course, the range is still minus 1 to 1. All the y values that are hit, everything between minus 1 and 1 is hit. Okay, tangent, we already said minus pi over 2 to pi over 2. And you'll observe that I can't include the endpoints like I did with sine because I have asymptotes at minus pi over 2 and pi over 2. That much we do know from when we were graphing. And now the range, well, what are all the y values that are hit by this curve here between minus pi over 2 and pi over 2? I think all of them, right? So the range is actually minus infinity to infinity. Cotangent, it's going to be from open at 0 to open at pi. And its range will also be minus infinity to infinity. So please look at the graph of cotangent. That's in a previous video. The secant and cosecant get a little bit more confusing, but let's look up here. So the secant is the reciprocal of the cosine graph. And let's see, what do we know? We know that the cosecant graph would have asymptotes everywhere the cosine equals 0. Okay, and so then the graph kind of goes like this, and like this, and so forth, right? Well, not my best drawing, but there we go. So what we're going to do is actually we're going to use from 0 to pi over 2, but open at pi over 2, so just this right piece going up, and then this left piece going down, then from open at pi over 2 to closed at pi. That'll be our restriction on the domain. And now the range, well, let's look. This piece that goes left and down here, that hits everything from minus infinity up to minus 1. And then this piece here hits everything from 1 up to infinity. So I think the range will then be like so. And for cosecant, again, we're going to restrict the domain. That's what all of this means here, right? Well, if we look at the graph here, we get asymptotes everywhere that the sine graph equals 0. There, right down at x equals 0. And so our graph looks something like this. And what we're going to pick is this piece here. It's from minus pi over 2 to 0, this piece that goes right and down, and then this piece here that goes left and up, so from 0 to pi over 2. And you'll notice it has to be 0, or open at 0 because there's an asymptote there. And then the range is actually the same, right? You get everything from minus infinity to minus 1, and then everything from 1 to infinity. Okay, so now we can now define the inverse trig functions because we have restricted the domains to where they have where the trig functions are 1-to-1, and so therefore they have inverses. And here's what we call them. What we call them is arc and then whatever the name of the trig function is, or the name of the trig function with a superscript -1. I tend to prefer the arc notation, but you'll notice since it's the inverse function, these two columns get flipped, right? So the range of the original trig function becomes the domain of the inverse trig function, and the domain of the restricted domain of the trig function becomes its range, the range of the inverse function, right? And so let's see what this is saying. This is saying that the arc sine function, it takes in values from -1 to 1, and it returns you an angle from minus pi over 2 to pi over 2. And so looking on the unit circle, the arc sine function, it returns an angle in this span here, from minus pi over 2 to pi over 2. So your answer is in quadrants 1 or quadrant 4, right? And now let's see what arc cosine does. Well, it takes in a value between -1 and 1, and it spits out an angle from 0 to pi. Well, those are quadrants 1 and 2, right? So your answer here in Q1 or Q2. The arctangent does pretty much the same thing as arc sine. Only thing is you don't allow the possibility of angle minus pi over 2, which is straight down, or pi over 2, which is straight up, because you have asymptotes in the tangent function. Arc cotangent does the same as arc cosine, right? Only you don't include the angle 0 or the angle pi, again because of asymptotes. And then the arc secant, it's essentially going to be the what the arc cosine does, only you don't include, you get like a you don't include the angle pi over 2. And then same with arc cosecant, only now you don't include you don't include the angle 0, but your answer is still in quadrant for arc cosecant quadrant 1 or 4. So maybe I'll write this down. Arc secant, your answer is in Q1 or Q2. Arc cotangent, Q1 or Q2. And let's say arctangent, your answer is in Q1 or Q4. And that's going to be important, so make a remark, or maybe put a star next to that or something. Okay, so let's do a couple easy examples here just to get started, and then we'll do one more short video where we do some more maybe complicated examples. So here, this first example, the inverse sine or the arc sine, however you want to read it, of square root of 2 over 2. So this is asking for what angle in minus pi over 2 to pi over 2, so in quadrants 4 or 1, do we have a sine value of square root of 2 over 2? And it may take a little bit of thinking about it to see, but the angle is pi over 4, right? Because the sine of pi over 4 equals root 2 over 2, okay? So now let's try this one. The arcsine of minus 1/2. What angle in quadrant 4 or quadrant 1 has a sine value of minus 1/2? Well, I think that's minus, what do you think? Pi over 6, right? So if you, like this angle right here, right, has a sine value of minus 1/2, right? Okay, so now when you have compositions of trig and arctrig functions, you want to work inside out here. So first let's find the arcsine of 1/2. Well, if you look here, the arcsine of 1/2 is going to be pi over 6, and so we're plugging that into this sine function. And so now we're getting the sine of the arcsine of 1/2 is really the sine of pi over 6, which is, well, 1/2, right? And so, in fact, you can write this down and take it to the bank. If you have trig function evaluated at arctrig function, then they actually cancel each other and you just get the inside. The other way does not work, but this way does. And in fact, sometimes the other direction works. So notice we have arctrig of trig. Sometimes it works. So sine of pi over 4, well, that's root 2 over 2. So this is sine inverse root 2 over 2. Oh, but we already know that look up above. That is pi over 4, right? So in this case, arctrig of trig canceled each other, but sometimes they don't. Let's look at this example here and maybe put a star next to these two. So this is arcsine, and now what is the sine of 2 pi over 3? Well, that is square root of 3 over 2, right? And now this is asking for what angle in quadrants 1 or 4 have value square root of 3 over 2. And the answer is pi over 3, right? And so the reason this one didn't cancel each other is because the angle was not in the right quadrant, right? 2 pi over 3 is in quadrant 2. The arcsine value will never return an angle in quadrant 2, only in quadrants 1 or 4. And so that's why things were different there. Okay. All right, cos inverse of minus 1. So what angle between 0 and pi has a cosine value of minus 1? Hopefully you know that that's angle pi. What angle in minus pi over 2 to pi over 2 has a tangent value of 0? Well, I mean, you can even look at the graph and see it. Here's minus pi over 2 to pi over 2. What angle has a value of 0 when you do the tangent of it? Well, angle 0, right? Okay. Here we have trig of arctrig, right? So we don't even need to know anything. Automatically get 12 here. The only thing that you have to check really is that this number is in the domain of the proper arctrig function. So the domain of arcsecant, are we allowed to plug in numbers bigger than 1? Yes, right? So as long as the number is in the proper domain, trig of arctrig always cancels. All right. So I think what we'll do is we'll end it here, and then we'll come back in the next video and finish up the examples.